Shukla here, and this is a submission for Google Tunix Hackathon, teaching Gemma how to think, a GRPO-based Tunix fine-tuning pipeline. Let's start with the challenge. As we know, the today's large language models are highly competent and very good at solving problems, be it math, puzzle, logic, even coding tasks. But in many cases, they give the final answer without clearly explaining how they arrived there. This becomes an issue in open-ended domains where there is not a single correct answer, and the evaluation depends heavily on the quality and structure of reasoning. So the goal of this project and hackathon is to fine-tune a model to explicitly show its reasoning in a structured and reliable way. Let's start with the dataset that I used for fine-tuning. So I used OpenThought's reasoning dataset from Hugging Face. It includes around 100,000 plus records covering math, science, coding, and puzzles, with each problem, a verified solution, and a reasoning trace. But as you can see in this diagram, there was a lot of class imbalance. Math and code samples dominated the dataset, and there was an imbalance in the token length for the prompts as well. So I trimmed out the examples with overly long inputs to avoid memory and token budget issues. I balanced the samples across domains so there is no single domain which dominates the learning signal, and prioritize examples with ground truth to ensure high quality supervision. At the end, I split the dataset into 80-20 train and test split, so the evaluation reflects the performance across all types of problems. Next, coming to the reward functions I used. I started out with 7 reward functions, first being keyword-based logical coherence reward, 2 of them being format reward, then the LLM as judge, length reward, and structured causality reward. But as I experimented with this, I faced some challenges. With the keyword-based logical coherence reward, I noticed it quickly observed reward hacking behavior. The response correctness degraded and the keyword repetition increased. Similarly, with LLM as judge, it did improve the correctness, but the training time increased by a lot. So I kept the 5 reward functions at the end and added a composite function which includes all of these 5 reward functions and aggregates all of them based on a particular weight. Next, let's talk about training and ablation insights. So for hyperparameters, I experimented with quite a few hyperparameters like beta, learning rate, generation length. But as I experimented, I observed a few things. For example, with beta, lowering the beta increases the chances of rewards, but also increases the chances of reward hacking. For example, as we can see in this plot, the rewards did consistently increase at each step. But as I looked at the responses generated, I noticed that the actual accuracy of each response consistently dropped. So at the end, for the final training configs, I decided that the moderate KL penalty with beta of 0.08 gives stable learning, too low cost policy drift, too high suppress the learning. And these insights informed final configuration and highlight the trade-off between quality, compute, and stability. Next, let's talk about the results. This table here shows the before and after training metrics. For the mean, it improved from 32 to 66, that's 34% improvement. For the median, it improved quite a lot from 33 down to 0.7, that's 26% improvement. Overall, the GRPO reward component improved by 34%, that is the accuracy of composite reward functions across all the 5 different reward functions. Talking about the formatting accuracy alone, it improved by 95%. In summary, this shows that the well-designed reward functions and structured prompts can teach a language model to show its work. That's it. Thank you.